Okay, this is Tom Cox. I'm currently representing IDOT District 6. We've got this I-55 reconstruction project from Avenue to north of Sherman. Today we're just going to be taking a look at the Sherman Interchange from Andrew Road to Sudeth Road. The reason for that is it has to do with the profile of the main line on this interchange. Currently, the proposed profile is very similar to the existing profile. It's just a little bit higher. But we actually need to take a look and do a comparison of the impacts of raising that profile 3.25. And the reason for this exercise has to do with actually these piers here. We've got, this is Business 55. We've got the railroad running under the structure, and currently the piers are on the existing railroad right-of-way. And also currently the plans are to replace the structure, the piers, at the same location. And we can take a look at that here. There, as you can see, the railroad right-of-way is 50 feet wide on each side of the railroad, and you can see that the current plan is to place the piers in the same footprint as the existing. The situation is that the railroad would prefer that the piers be off railroad right-of-way, and so IDOT needs to take a look at what that would take and what the impacts of raising that profile would be. And so in order to do that, we use the ORD software, modeled the entire interchange, including both the main line, the bridge itself, and then the 3 interchange ramps. We're then able to store a profile that gave us enough clearance above the railroad track to the low beam elevation, and we did a cost comparison. And we primarily we're not looking at every single pattern. We're really just looking at the main impacts, and that main impact would primarily be the earthwork, the additional fill, the additional height on the retaining wall, and then the additional structure cost. So let's take a look at how we went about that. What we did was we just took the existing profile, kept the same VPIs, which are near Andrew Road and Sudeth Road, and then we just increased the elevation of to give us 3.25 of additional clearance. We kept the same vertical curve length. We then make that the active profile, and then we apply our templates against that profile, which then produces a 3D model within multiple corridors, and then the corridors will give us the earthwork calculations. Okay, so let's take a look at the 3 or 4 templates that we used on this interchange. Okay, so this is, actually that's our second corridor. Let's take a look at the first one. So this is the template that we applied against the first corridor. What we have here is the roadway PGL is located 17.5 feet from the center line. So we end up with a total 16-foot shoulder, and then three 12-foot lanes, the first being 1.5%, the second 1.5%, the third then 2%, with the outside shoulder being 4%. The pavement type is PC, 4 inches of BAM, and then we've got another 12 inches of subbase. On this first corridor, we've got an MSE wall, and that MSE wall targets the existing ground and then goes down an additional 3 feet. Let's see. The second template that we're going to be using is north of the bridge, does not contain an MSE wall, all the same widths. The difference being you've got this barn type four-slope where we go out at a 1 to 6 from the edge of, or 30 feet out from the edge of pavement to the clear zone, and then we end up with a 1 to 3 down to the existing ground. We also have some additional pavement to handle the ramp, the southbound entrance ramp transition. We also modeled the bridges. The bridges have the same, are basically the same as the roadway. That inside PGL is 17.5 feet, the same as the roadway. There's no jog in it. Of course, the bridge has to be wider at the southbound entrance ramp, and so that's why you see this bridge on the left being wider than the one on the right. We've got a beam depth of 72 inches. And when we're first going to run this against the corridors to get these quantities first, and then we'll come back, we'll change that to the 33 inches and adjust the profile. And then lastly, we've got we have the ramp template, and there we've got 16-foot pavement. We've got 6-foot shoulder on the inside. We've got 4-foot shoulder on the outside. And that's, like I said, 10-inch PCC, again with 4 inches of BAM, 12 inches of subbase. Again, we've got that barn style four-slope where we go 1 to 6 out to the clear zone, and then 1 to 3 down to the existing ground. So those are all the templates that we're going to use. So I'm going to close out of that. And we'll just take a look at this very first corridor from Andrew Road up to the bridge. And we'll move in. We'll go ahead and visualize a cross section somewhere close to the bridge. And you can see our situation here. Again, this is, we're looking at raising that profile 3.25 feet. So again, the top profile is the active profile. So then that's what you're seeing here. That's that blue dot right in the middle. And then the inside edge of pavement that is 17.5 feet out is the same elevation then as the PGL. So we go ahead and we apply that template that we just looked at against the south corridor. And then after that, we ran our super elevation. Turn that on for a second here. The super elevation. This is the north one anyway. And we calculate our supers, which includes both, the pavement itself plus the rollover for the shoulders. And includes transitions. So given this radius and design speed, we ended up with a 6% cross slope at a 75 mile per hour design speed. Okay, so let's take a look down here at the cross section, and you can see that in the model up above. There's the MSE wall. You can see with raising the profile, we end up with an MSE wall height of, at least at this station. What do we have here? We'll measure that. So 11.2 feet. So that's, again, much higher than the other profile. So that's part of where that additional cost is going to be in all this additional fill, and then the raising of the MSE wall. And that MSE wall runs almost all the way to Andrew Road and then ends at the bridge. And so then what we do, once we've processed this, then we can just go into our corridor reports. We can select that full corridor, and then that will give us our volumes, so our cuts and our fills. And you can see in this case we got 5,500 cubic yards of earth excavation and 43,000 cubic yards of furnished X. So we plug those into our quantities, and we'll come back to this later. Okay, so that's how we go about calculating our quantities. Again, as far as the impacts go, let's take a look at these ramps real quick here, because really that was a big part of the impact. You know, not just the main line, the additional fill that's required here. Let's take a look at the southbound, both entrance and exit ramps. We can go ahead and visualize a cross section on those ramps. And then if we look at the ramp somewhere close to the main line, you see how high the ramp would need to be. And let's also take a look at that ramp profile to see why it needs to be so high and why we need so much additional fill at this location. Okay, the profile on the top is, again, what it takes to raise the profile on the main line, 3.25. So that's what you're seeing over here. And so, you know, like I said, it's also taking into account the super elevation that is required on this curve. So in addition to the 3.25 feet, we still get a little bit more height because of that super elevation and the breakover. But if I was to take this inside edge of pavement, and what I can do here is I go to my geometry tools and I can project this edge of pavement onto this profile, and that's what we're seeing here. So it projects that profile, and then what I do to get tied back in to finish that profile, that ramp profile, is I just extend a tangent line, which I've got the tools to do that here. From that profile, I extend a tangent line, and then I try to get tied back down just as soon as I can. Here we end up with a 3% on the ramp currently I've got a 500-foot vertical curve. We can tweak that a little bit as needed, but to get some, good quantities, that, for what we're looking at right now, this is more than enough as far as the level of detail and degree of accuracy. There can be a little bit of tweaking, but it really gives us, looking at the concept in this way of the modeling an interchange, like pulling those quantities, and then getting that total quantity, and that's with all the corridors, both the corridor on the south side of the bridge, north of the bridge, all three ramps. Then we get our total, so we have our total cuts and fills for each one of those. And then from that, we can look at, pay items required, because that's how we're going to figure the cost, and that's going to be based on the earth excavation pay item and the furnished ex pay item. So let's just take a look at these two real quick. You can see that with the first profile, which again is very close to the existing profile, the earth excavation and the furnished ex pay items are relatively small. Actually, the earth excavation is a little bit greater than raising the profile, but where really all the cost is, and you can see this huge difference in the furnished ex, that additional fill to raise the mainline roadway, and the ramps ends up being 136,000 cubic yards. And so when you look at the additional cost, what we do is we just take that 136 minus the 24. So you can see that we're looking at well over 100,000 additional cubic yards of furnished excavation, and add a minimum of $30 per cubic yard. That's a substantial amount of additional cost just in the earthwork alone. Next, we compared the MSE wall height, and so the lower profile, the original profile, we end up with 14,000 square feet of MSE wall. With raising the profile, it adds an additional 5,000 square feet, and then in addition to that 5,000 square feet, it's also of the structure type, you also end up needing MSE walls down along Business 55. And so when I look at the quantity of each of those MSE walls, and I get that total, the 5,000 difference plus the 6,000 plus the 5,000, again, you can see we have a substantial amount of additional quantity and cost of the MSE wall. The last big item that we have not looked at yet, that we're getting ready to look at next, would be the additional cost of the structure, with going with the 6-foot girders versus the 33-inch beams. And so we'll see what that total cost difference is. But for this portion, the roadway portion, again, this is just a quick demonstration on how we used the ORD software to do a cost comparison against those two alternates, and really a very efficient period of time. And that's all I have for today. Thank you.